again, Nicole, for your talk. And as for me, it will be my presentation will be about feedback couplings for acoustic scattering using feedback. And it is the result of an internship I have done at INWIA, for which my advisors were Marcela Bonazzoli, Xavier Claes, and Pierre Marchand. I will set in the first quick part the scientific background and the motivations of my talk, and then I will explain how to derive boundary integral equations. After that, I will use them to express feedback couplings, and I will show how to implement them numerically in paper. So my work consists in studying waves equation, and a wave is characterized by its strength lambda, to which can be associated a wave number k, 2 pi over lambda, which is positive. And in real life, waves have many applications, such as localization of obstacles by the sonar, or non-destructive testing of buried infrastructures. And in all the talk, I will focus on acoustic waves, which satisfy the Helmholtz equation, Laplacian u plus k squared u equals 0. And on the right of the screen, you can see the total field as a scattering of a plane wave by the disk, where the plane wave is coming from the left. And it is a result obtained with free fall. In all the talk, I will work with the case of scattering of an incident plane wave by an impenetrable obstacle D, and I will assume that the rest of the domain that I call omega is homogeneous and non-dissipative, which means that the wave number k is constant and real. And I will name the scattered wave u. And it is well known that to get a well-posed problem, since the domain is unbounded, we have to have two boundary conditions, one on the obstacle, and in all the talk I will choose Dirichlet boundary conditions, and also a radiation conditions, which eliminates unphysical solution. But still, this problem is challenging to discretize because the domain is unbounded. So there is a solution when we work with homogeneous domains, which consists in reducing the problem on the interface gamma, thanks to boundary integral equations. But it's not, we cannot do this when we work with heterogeneous domains. And when we have domains with heterogeneous and homogeneous subdomains, we will use Feynman couplings. So the idea is to write boundary integral equations on the omega x, the volume parational formulation on omega int, and to couple them with transmission conditions on the interface. And this is what we call Feynman coupling. And in the talk, I will present the implementation in 3Fem of different Feynman couplings, and I will establish a comparative study for increasing wave numbers. But before doing that, we need those well-known boundary integral equations. And it is well known that when we have when k squared is constant in the Helmholtz equation, there is a fundamental solution, G. And thanks to it, we can derive two potentials, a simple layer 1 on the left and a double layer 1 on the right. And with this potential, we can express a representation formula which allows us to represent the solution in the whole domain with only the knowledge of the Neumann trace gamma n and the Dirichlet trace gamma d on the interface. And we mark that the potential, the simple layer and the double layer, provide solution in omega, but also in its complementary. And then by taking traces of these potentials, we can derive four boundary integral operators, which are the single layer, the double layer, the adjoint double layer, and the hypersingular. So I do not give the expressions of them because I don't have the time. But just remark that when we denote the quasi-adjoint operation by a star, we have k star, which is equals to minus k equilibrium. And when I use the Neumann trace, my outgoing normal is entering in the obstacle. It's a choice, and so maybe if you know boundary integral operators, it's not the same definition that you are used to. And thanks to the boundary integral operators, we can define boundary integral equations. So there are two ways of doing it: a direct approach and an indirect approach. And I will begin with the direct approach. So we start with our representation formula, and then we apply either Neumann or Dirichlet trace, and we can derive two boundary integral equations known as Calderon equations. And remember that since we work with Dirichlet boundary conditions of the obstacle, the only unknown is the Neumann trace in both equations. So that's why we call it direct approach, because we obtain directly the unknown trace. But there exists another way to derive boundary integral equations, which is the indirect approach, and which consists of searching a solution as a potential applied to an unknown density phi. And then you apply the trace which corresponds to the non-boundary conditions that you have on your boundary. And here in directly, we derive two boundary integral equations, but we could do it if we were working with Neumann boundary condition, and we will obtain two more equations, which are really linked with the Calderon one that was just before. And just remark that for each boundary conditions, there are a first kind and second kind of equation. And I will use this fact to name at the end of the talk the numerical results. However, it is well known that well-posedness of Helmholtz problem depends on boundary conditions and boundedness of the domain. And even if the volume problem is well posed, previous boundary integral equations can be ill-posed. And it's really an issue. And the solution is to work with combined boundary integral equations. If the volume problem is well posed, combined boundary integral equations will always be well posed. And what I call combined is when we work with an eta complex with real part different from zero, and we combine either for direct approach Calderon equations, so the fact that we combine is seen here by the apparition of minus I eta, or when we combine in indirect approach, we combine the ansatz, and it appears one more time minus I eta. And so we have new operators, new boundary integral operators A and B, and you see on the left for direct approach we have A, and for the indirect approach we have its KG adjoint. Okay, so now we have all our boundary integral equations, so we can write our Fembem couplings. Remember that we want to write boundary integral equations on omega x, or volume variational formulation for omega n, and we want then to couple them. And the goal is to treat both domains with by exploiting the advantages of both Fem discretization and Bem discretization. For Fem, it's the fact that we can discretize an heterogeneous domain, but it leads to large sparse matrix. And for Bem, we can discretize an unbounded domain, but it leads to small, because we have reduced the dimension by one, dense matrix. Okay, so I will work on a toy object for the end of the talk, which is the scattering of a plane wave by an elliptical cavity, and all the domain is homogeneous. And to have two domains, I just choose a circle large enough to include the obstacle, but I still solve the scattering problem. So we have the same equation in omega x and in omega e. And of course, we still have Dirichlet boundary conditions on the obstacle and radiation conditions. But we add our transmission conditions, which simply express the fact that we have conservation of the field through the interface and conservation of the flow through the interface. And we add our rational formulation that I have spoken previously. So it will be too long and too time consuming to explain how to have all Fembem couplings formulations. So I will just explain you how to do it when we work with an ansatz, a simple layer ansatz, which is known as Vleiak-Makami coupling. So first, we start from our ansatz and we apply Dirichlet trace. Then we inject the first transmission condition, which expresses the fact that the interior Dirichlet trace is equal to the exterior Dirichlet trace. And once we have done that, we introduce test function to derive a variational formulation. So this is our first equation. Then for the heterogeneous domain, we start from the variational formulation, which is reminded on the top of the screen. We inject the Neumann transmission condition, and then we inject the second boundary integral equations that we can derive since we have chosen a simple layer ansatz. And we derive our second equation. And here I have written in red the unknowns of the problem. And remember that we have two equations and two unknowns, a volume one U and a surface one phi. So we can derive other Fembem couplings for when we choose other ansatz, and I will call them numerically ansatz SL, ansatz DL, and ansatz format. And we can also do it for direct approach, and I will call them direct HK. So as first kind, direct SK as second kind, and for the combined boundary integral equation, I will say direct combined. So in the Riemann that we work with the polar scattering by an elliptical cavity D, and I have chosen an incident wave with an angle alpha equals to 4 pi over 10, which means that the wave is coming like this and can enter in the cavity. And I have also worked with distributed memory parallelism on acres. And since we are in FFM days, I have worked with FFM, and especially with recent features of FFM, but I have not implemented the boundary integral operators. I have used the BAM tool library with P1 surface elements, and also the H tool library, which is really useful since we work with dense matrices. And for the linear system, I have solved it with the TMOS, so you can remind the presentation of Nicole, and also with PETSI, if for those who have followed the advanced class yesterday afternoon. And I have also used the composite finite element spaces combining mesh, which is a volume mesh, and mesh and meshes, which are surface mesh. So FEMM coupling can be written in a condensed way like AB and GQ, and solving such a coupling amounts to solve a linear system Mx equals F, where M can be seen as a matrix made of 4 blocks, MA, MB, MG, MQ. So MA is sparse, since it's the matrix associated to the FEM part. MQ is dense, since it's the matrix associated to the boundary integral equation. And MB and MG can be sparse depending if we are working with direct or indirect approach. And to conclude the talk, I will present 2 numerical experiments. One with GMOS without restarts and with a white elliptic conditioner on MA and MG blocks. And the second one with restarted GMOS this time and still white elliptic conditioner on MA and MG. And here just you can see what looks like a solution for wave number K equals 16, and you can see that the wave has entered in the cavity with some resonance. Okay, so before showing you the implementation of FEMM couplings, I wanted to show you the implementation of just a BEM problem, because you will see that it is as easy as writing BEM coupling than writing FEMM coupling. So first, we define our mesh, our surface mesh, and we orient the normal. Then we define our finite element space, and we define the variational formulation. Once we have done that, we can define our associated matrix. And remark that when we write int 1D x1D, it means that we have a double integral. We have a double integral since we work with a variational formulation. So the first integral, and the second one comes from the definition of the boundary integral operator, so V. Oh. So now that we have defined our matrix, we can define our right-hand side also. And then we solve the problem with the free-frame notation. So really easy. And it's just the same for FEMM couplings. So we define our meshes. So we have 2 meshes, volume 1 and a surface 1. The volume 1 is for the heterogeneous domain, and the surface 1 is for the interface. We define our finite element spaces, and then we define our composite finite element space. So remember that it's just like a Cartesian product in mathematics. Once we have done that, we can define our variational formulation. So if you remember what have been shown yesterday, we have to use these brackets to say that we are working with a composite finite element space. And then we simply write our variational formulation. So the first term is the top left term, our volume integral. The second one and the third one at the top right term. So we have a first integral involving just the identity, and the second one involving a kernel. So it's a double integral term. And then we have our bottom left term, our bottom right term, and we enforce the Dirichlet boundary conditions because we have chosen the Dirichlet boundary conditions. Once we have done that, we can define our associative matrix. So here we can work either with PET-C or we have without PET-C. So that's why I have defined that one. But if you only work with PET-C, you have no need of the macro. And then we define our right-hand side. And one more time, we solve the problem with the free-frame notation. And we can split the solution into FEM and BEM solutions really easily by this, thanks to this side. So you can see that it's really easy to write FEM-BEM couplings now in free-frame. Before the latest release, it was not as easy. Okay, so here's just an example for you to be sure that the matrix is a sparse blocks, dense block, and a sparse block on the bottom left because it's indirect approach. If we were working with direct approach, we would have a sparse block here, and it would just be the transpose of the matrix. However, solving such problem without preconditioning is too time expensive. And we need to precondition M, and it's really easy in free-frame to do it, thanks to PET-C. So we can put a precondition either MA and MG blocks, MB or MQ blocks, or the 4 blocks. But since here I work with a FEM LU preconditioner, I will only precondition MA and MG blocks. And what is important in this slide is written in red. So remember that since we work with composite finite element space, we have to say to work with field split when we want to precondition. And we say that on the first block, block 0, we want a preconditioner type LU. But we have to say that on the second block, the block 1, we have no preconditioner. And it's really important to understand this because it won't the code won't compile if we do not say that we have no preconditioner on the BEM blocks. Just before showing you my first numerical results, I just wanted to draw your attention on the fact that two direct boundary integral equations can be associated with indirect boundary integral equations thanks to the KGL joint operation. Because as you can see on the right of the screen, the involved operators have the KGL joint of the left operators. And since the KGL joint operator and direct one have the same spectral properties, we expect that the number of iterations is roughly the same. And it is what we observe without restarts. So when we work with when we look at direct first kind, so purple diamond, we observe that we have at low wave numbers the same number of iterations that is on that SL, which is its corresponding indirect approach. And it's also the case for second kind couplings and combined couplings. And what we also observe is the fact that the worst coupling is always the first kind couplings. But we cannot say so much for the other couplings. So even at high wave numbers, there's not a clear difference between them. But in practice, we never work without no restarts, and we work with restarted GMOS. And one more time, it's really easy to do it in free-frame. So before to say that we have no restarts, we have set the fact that our restarts were 12,000 because the maximum number of iterations is 10,000. And if we want to say to work like let's say 30 iterations, 30 restarts, we just replace 12,000 by 30. And we obtain the following results, which are really different. We still observe that first kind, so purple diamond, is really bad in terms of iteration. But we observe that direct second kind, so one plus, doesn't converge anymore at high wave numbers, whereas it was not the case before. But we observe that combined boundary integral equations, combined couplings, are really robust when we work with FEM-BEM couplings. And we started GMOS because they converge even at high wave numbers for only 100 or so iterations. So to recap it, without restarts, direct first kind leads to the higher number of iterations, whatever the wave number. And when we work with restarted GMOS and a preconditional FEM, we still have these parts, but the second kind coupling explode and phase to converge for high wave numbers. But for direct combined couplings, we have the best formulation. It seems to be the best formulations at high frequencies. To conclude, we have derived the Fembem couplings and observed that with only a preconditioner of Fem blocks, the combined formulations at the lowest number of iterations. So I have other results that I have not presented in the talk, which is the fact that these results still holds for other obstacles and other incident plane waves. And also we have one simulation by preconditioning Fem blocks and also both Fem and Bem blocks. We have seen that when we write the discretization in free Fem, it's as easy as writing them as writing them. And future considered works will consist in numerical study of other Fem-Bem couplings that cannot be currently implemented in free Fem, such as costable coupling or coupling implying impedance transmission conditions, and also numerical study of Fem-Bem couplings for problems with non-constant coefficients, because here it was just a toy problem, and also for problems in 3D. So I thank you for listening me. If you have any questions, it will be a pleasure for me to answer.
As usual, time for one question. As usual, Olivier. Pierre-Henri. Pierre Jolivet, sorry.
What precondition do you use for the pen block?
No precondition.
Yes, but here you said not presented in the talk.
GMOS one.
This is the prior song. As you
We apply a first GMOS on them blocks, and then a second GMOS for the whole matrix.
okay.
It's very difficult when the coefficient in the two domains are very, very different, which is often the case. Have you tried that?
Oh no, but it's something that we envisage to work with.